And so, Luca Vizioli, we're very happy to have Luca here in Boston. He's a pioneer of this not only super duper high spatial and temporal resolution fMRI, including laminar, but also has shown us, a lot about how these sophisticated denoising methods can really help us to improve our data. Also, I hope that Luca is going to show us some data from the 10.5 scanner that he's been, if he has time. Okay, so let me give him the mic. Very good, thanks, Luca. So then, again, just gonna speak into here. Okay. On the other side. Yeah. Oh, you're good. So, sure. All right.
Thank you. Can you hear me? All right, great. Well, thank you very much, first of all, for the invitation to all the organizers, not only give me a chance to show some of our work, which we're very excited for, and also to have a great chance to interact with so many cool scientists and having a great time. So thank you so much. And you're too kind. It's not true at all what John is saying. So today I'm going to talk about denoising, looking at thermal noise denoising specifically, and the bulk of talk is going to be on Nordic. I'm going to give a very brief outline. So I'm going to start with a brief introduction just to frame the problem. And then I'm going to talk a little bit about the Nordic theory and how it works. I'm not going to spend too much time because it's all published, but just to give you again a general understanding of how the technique works. We're going to look at how we validated Nordic and how we made sure that it wasn't doing anything wrong to our data. Then we're going to look at the impact of Nordic on spatial precision, which is a big deal because obviously, we're trading, we're jumping through hoops literally to get as high as possible spatial resolution, and we don't want to trade that back in for cleaning our data from noise. I'm going to talk a little bit about Nordic on VESO, which is the work of Lasse, Knudsen, and Renzo. And I'm going to show you some practical tips on how to run Nordics, some of the optional arguments that you can input into the function, and some things that you need to be careful about. And if I have time, at the end, I'll show some of the applications Nordic to sub-millimeter fMRI, both at 10T and 10.5 and 70. All right, just a little bit of background. So fMRI has a inherently low signal-to-noise ratio and functional contrast-to-noise ratio. And we've heard over the last couple of days in Saskia's talk, for example, how different acquisition mechanisms lead to different sensitivity versus specificity considerations. But even in the highest SNR case, which is like gradient and echo data, once we're in sub-millimeter range, we are very much SNR starved, and we need to deal with this noise problem somehow. So thermal noise, which noise comes from instrumental noise, can be a prominent noise source in fMRI. And its contribution depends on the static magnetic field strength, voxel volume, image repetition time, and it becomes higher and higher as resolution increases. Obviously, it is directly proportional to the voxel volume, but it's also greatly affected by the acceleration that are required to fill in the big matrices, like Saskia was showing us yesterday when we go to higher resolutions. At 7T, there's people that argue that is the dominant source at 0.5 microliter voxel. Maybe we'll hear differently in the following talk, but which is like 0.8 isotropic voxel, which is kind of like our workhorse for sub-millimeter fMRI. However, even at 3 millimeters, lower field strengths and relatively long TRs, thermal noise can be detrimental for your data. So we tackle these challenges using a denoising technique that we developed a couple of years ago called noise reduction with distribution corrected or Nordic PCA, which targets thermal noise. As I said a little bit about how Nordic works. So Nordic is a local low rank approach. So it's a PCA-based approach. Instead of performing PCA across the whole images, we perform it in independent patches and then we recombine it together. And this is how it works. So you start from some images like this. First of all, we do some G-factor normalization. This is because while in theory, thermal noise should be spatially invariant, in practice it is not. It depends on many factors like distance from the coil and so forth. And so we need to account for this factor, enter the G-factor normalization. Then we extract information from our patches, and then we input into our Casorati matrix, which is just a fancy term for a matrix that allows us to rearrange the data in a useful way to then solve our singular bar decomposition. Then we go obviously our singular value decomposition, which is the basis of our PCA, and in the V matrix we have our eigen vectors. And we use singular value thresholding to determine whichever component is not distinguishable from Gaussian-like distribution. Our assumption is that, and we know that thermal noise is distributed, is Gaussian-like distributed with a mean of 0 and standard deviation of 1. So everything that cannot be distinguished by Gaussian noise is removed. We then perform the average across all the independent patches on which we have performed our PCA, recombine them, and then multiply by the G factor. Inject the G factor back in. So when we were thinking about Nordic and developing the technique and applying it to fMRI, we started thinking what would make a good denoising algorithm. So obviously a good denoising algorithm ideally would remove noise while leaving the signal intact. And therefore, in the validation process and to understand the impact of Nordic on fMRI, we looked at a number of metrics that are commonly looked at for fMRI, and we made some assumptions. Some should be perturbed and some should not be perturbed. So some of the metrics that we expect to be perturbed are positively perturbed, are SNR and, for example, t-values. So we expect an increase in those if we're doing a good job of removing noise. We also expect, with a caveat, an increase in the precision of response estimate. And I'll get to that in a minute. And then ideally, we want our response amplitude to be unaffected. So we want to remove the noise without actually affecting the signal. And crucially, as I mentioned, we don't want to see any loss in spatial precision. So to validate Nordic and understand the impact of Nordic on functional maps, we turn to the retinotopic properties of V1, which provide the ground truth as to the extent, the spatial extent of activation elicited by visual stimuli. And so this is the paradigm that we use, simple flickering gratings, counterphasing 6 Hz, a target condition and a surround condition, very standard 12-second on-off block design, where we had 3 repetition of each condition within each run. We acquired 8 runs. 2 runs were used to identify the retinotopic representation of the target in V1 and were excluded from further analysis. And then the remaining 6 runs were used as experimental runs. And as I said, 3 trials per condition. Each run was about 2.5 minutes. So the bulk of the validation we carried out on our 2D grain echo data. So it's 0.8 millimeter isotropic voxel with a TR about 1.3 seconds, and that's the same data that Renzo was showing yesterday. And we started from an easy case to the grain echo, which we know is one of the better BFKs. And so here we can see a single image API on the left as they come out of the scanner before Nordic, and then on the right we can see the same image after Nordic. And I guess that I hope that even just by visual inspection, you can see that, especially in the middle of the brain, further away from the coil, well, thermal noise is more prominent. Nordic seems to be doing a good job at cleaning it and getting rid of this speckly noise. Obviously, it's just visual inspection, so it's not that clear, I'm sorry. So we want to try and quantify this a little bit more, and we're going to look at the metrics that I just mentioned. So pre-processing was kept at a minimum, so just slice time, motion, and detrending. We didn't do distortion correction. I'll get there in a minute. That's because we didn't do any layers in the specific case, and we didn't really care about alignment with T1. We just wanted to preserve the spatial specificity as much as possible. And so skipping one interpolation step would be ideal in the specific case. And then we computed like standard TSNR, just mean of the signal with the standard deviation of the signal. And we got here for 2 example subjects, 2 slices, an anterior slice, and an occipital slice that includes the retinotopic representation of the target. And you can see that the SNR increased for Nordic, which for both subject and regardless of the area you're in, can be up to 3-fold in this case. That's good. We want to see the TSNR to go up as we clean the noise, standard deviation goes down. That's good. But that doesn't really tell us much about the impact on Nordic on functional responses. So to start looking at how Nordic impacts our functional map in terms of precision and quality and extent of activation, we started by performing a very simple linear contrast, target larger than surround, and we looked at the T values, the T maps for this contrast. So T maps can be very loosely defined as the percent signal change over the model error. So the noisier the data, the lower the T value. And so here's an example of this T maps. So in blue, you see the activation to the surround. In red, you see the activation to the target. This is like an infrared cortical representation of the occipital cortex. This is the calcarine sulcus, and this would be the retinotopic representation of the target for one Nordic run and one run of standard data. And then we computed the same type of target with a number of concatenated runs. In this case, I'm showing you 3 and 5, and then repeated this across our 4 subjects. And we see that the extent and quality of activation achievable with a single run is significantly superior that of Nordic run, is significantly superior of that achievable with a single standard run. And in this case, we actually needed 3 to 5 concatenated runs to achieve comparable functional map qualities. So next, we looked at some region of interest-based analyses. So for this purpose, as I said, we looked at the retinotopic representation of the target, which was computed again with the contrast target larger than surround, and getting the voxels that are significantly larger than 0 at a given threshold. And here's an example of this region of interest in pink over a T1 image for 2 subjects. And then we went to look at all the single voxels for each single run for our 2 subjects, for Nordic in blue and standard in red, and the single voxel are these gray dots. And we can see that for all runs, we have significantly larger T values for all voxels within the ROI for Nordic compared to standard. Again, that's good. But the crucial aspect is here that these values are going up not because the signal intensity is going up, but because the noise is going down. So we looked at the percent signal change responses in the same region of interest for both Nordic and standard data, and we see that these remains largely unaltered. So that's great news. It looks like Nordic is doing a really good job at removing the noise while not really meaningfully impacting the signal. There's a different way to look at the data. So same data set, the gray dots represent single voxels within the retinotopic representation on the target. And here we're looking at the T values on the left and percent signal change on the right. And the scatter plots are Nordic data on the y-axis versus standard data on the x-axis. And as you can see for all runs and for these 2 subjects, we have T values being significantly biased towards Nordic rather than standard, while instead the percent signal change estimates lie very close to the line of unity, indicating high correlation and correspondence between voxels. So I like this plot because in the plot that I showed you before, we couldn't really see voxel to voxel correspondence. And here instead, obviously, we have voxel correspondence in the scatter plots. Okay, so the other thing that we want to make sure that is improved with Nordic is the precision of response amplitude. So the assumption here is that, especially with the stimuli that we're using, flickering gratings, in a noise-free world, several presentation of the same stimulus should lead to comparable evoked response, if not identical evoked response. Ideally, without feedback, it would be identical. So the assumption is that if we were to estimate single trial responses and then look at the standard deviation or some sort of variance estimate for this single trial, we should see that these decreases after Nordic. And this is exactly what we see here, again, within the region of interest of the retinotopic representation of the target. We see that the standard deviation within each run of the single trial estimate decreases for Nordic estimates. And so this kind of tells us a little bit that the precision of the single trial responses is increased, or the variance is decreased using Nordic. Another way to look at the precision of the response estimates, something that we like to do quite a lot, is looking at model cross-validation, very simple model cross-validation. So we can compute our GLM on a given run, estimates our beta weights, our parameters with standard least square residual stress. And then what we can do is we can multiply the betas that we've derived in run 1 by the design matrix of run 2. And that would tell us that we compute our model for the second run based on the prediction of the first run, and we can see how well these models fit the second run. And that's what I'm showing here. We got the model in the darker run for Nordic, and this is the time course of run 2 for a single voxel, so model computed by multiplying the design matrix of run 2 by the percent signal change of run 1. And this is for Nordic and standard data for subject 1 and this subject 2. This one here is a highly specific target voxel. This one here is a voxel that lies at the edge of the region of interest. There's a little contamination from the surround, as you can see here and here. But regardless of the voxel that we're using, we can see that and the subject, we can see that the cross-validated R squared, so our variance explained, is significantly larger for Nordic data than standard data, again, indicating higher precision of, higher prediction accuracy and precision of estimates. And then the same way to look at this, now we're just looking at the maps, and we can see that this increase is highly localized within the retinal representation of the target, so spatially constrained in meaningful regions. So yeah, higher precision for Nordic denoise images in estimating response outcomes. So far, we only looked at ideal case, block design, MV1 with flickering ratings where everything is great, we create echo data, and everything is very, very well behaved. But how does Nordic generalize to different experimental paradigm, acquisition protocols, cortical regions, and stimuli? So here's an example of Nordic application to event-related design. This data from Federico De Martino. Very comparable acquisition protocol. The TR is a little bit longer, just because there was a gap to allow stimulus presentation during a quiet time. So it was auditory stimulation. And again, comparing the T maps, you can look at the activation in the auditory cortex, and one run of Nordic, one run of standard, and 3 concatenated runs of standard, sorry. And here we needed more or less 3 runs to approach the extent of activation achievable with a single Nordic run. And now here is a different region, different acquisition paradigm, and different experimental paradigm. We're using phases, fast event-related design, 2 seconds on, 2 seconds off, followed by a variable jittery ISI. The sequence is the HCP sequence 70, so 1.6 millimeter isotropic, 1 second TR. But in spite of being super millimeter and relatively coarse resolution, we still have a relatively high acceleration factor. So there's a combined acceleration factor of 10, leading to some thermal noise. So Nordic has a very much of a beneficial impact on this type of data as well. And now we're looking at ventral cortex, a little bit more challenging to look at. This specifically is the fusiform face area. And we can see not only that we need several runs, again, as we've seen with the other data set of standard data concatenated to approach the extent and quality of activation that we can achieve with Nordic, but we can see that even outside of retinotopic areas, like here, if you look at the spatial correspondence between 4 concatenated runs and 1 run of Nordic, it's very high. So that's really making us feel quite secure about not doing anything wrong to the signal. And I can look a little bit at 3T, so lower field strength. Went back to our favorite paradigm, 12 seconds on off gratings in V1. Again, we looked at 2 different sequences, the HCP 3T sequence, 2 millimeter isotropic voxel with 800 milliseconds TR and multiband of 8. And then a high resolution one, 1.2 millimeter isotropic voxel, 2 seconds TR. Now we got multiband 4 and IPAT of 2. And for both acquisition, we can see again that we're replicating what we saw with our sub-millimeter 70 gradient echo data, where we need several concatenated runs of standard data to approach the extent and quality of activation achievable with a single Nordic run. And again, I'd like to point out the similarity in the pattern of activation that you can see with several concatenated runs and one standard data and one single run of Nordic data. So just a very brief summary of what we've seen so far and what we talked about a little bit. So Nordic is a local low rank approach that removes component indistinguishable from Gaussian noise, from Gaussian distribution. In doing so, it increases the TSNR and T values of data and leaves the percent signal change responses largely unaltered. And it can be beneficial across cortical areas, acquisition protocols, experimental paradigms, and field streams. Okay, next I'm going to talk a little bit about spatial precision, which to me is one of the most important aspects. As we've discussed, as John pointed out, and as we've seen these days, we want to really preserve it to make the most of this difficult data that we're acquiring. So one way to look at spatial precision, in our case especially, because we've got this concentric visual stimuli in V1, is again exploiting the retinotopic properties of V1 to compute what we call functional point spread function. It's very intuitive, rather simple. Again, we perform our contrast target larger than surround to identify the empirical medial most border of the target. So in red here, we see the activation of the target on a flattened surface. In blue, we see the surrounding gratings of the surround. And here, where the voxel have activation of 0, that is our empirical border. Then what we can do is look at the activation elicited by the target only and superimpose this empirical border, which we derived from the contrast image before. And the idea here is that with an infinite spatial precision, as soon as we reach the border, the medial border of the target, we should see ceasing of evoked responses, because that area should be outside of your receptive field. It should not be stimulated. Obviously, we know that this is not the case. And so quantifying the fashion in which your percent signal change decreases as a distance from this empirical border will provide information as to the functional spatial precision of our data. So to quantify this, we can draw some perpendicular traces perpendicular to this empirical edge, and then we can fit some point spread models, point spread functional models to the data. And our model is very simple. That's just replicating what Amir Shmuel did in 2007. Stepwise function representing our infinite point spread. So once we get to the edge of the target, there's complete ceasing in evoked responses. And this is convolved with a Gaussian point spread and the full width of max of our Gaussian point spread, which is one of the parameters we're going to be estimating. And it's going to tell us how precise is our functional response. Good. I broke it. Did I break it? Too hard. Sorry. And here are the results of our point spread functional measurement for Nordic and standard data for two of our subjects. And we didn't observe any meaningful differences. So that's great. One was a little larger, one was a little smaller. But overall, nothing was significant. So that's great. It doesn't, in this specific case, at least, we didn't seem to observe any blurring induced by removing our thermal noise with Nordic. Obviously, not all studies can perform functional point spread function. You need to be in V1 with very specific stimuli and so forth. So there are other ways to estimate your spatial blurring. Taken alone, they're not ideal. So I would advocate caution in interpreting this measure alone. So this is like spatial autocorrelation, and it can be computed in AFNI. There's a very simple command line that allows you to do that. This was the work of Logan Dowdell, one of our postdocs. And basically, this measure tells you how much correlation there is between one voxel and the surrounding voxels. If you do this properly, this can then allow you to interpret the result as estimated smoothness of our data. And so here we can see this estimated spatial autocorrelation or smoothness or image blurring of our data for our four subjects, for Nordic and standard data. And again, we didn't observe any meaningful differences in blurring here. So again, that's good. But what are we really removing with Nordic? So understanding what we're removing is important. And also will give us further indication of whether we are causing any blurring to the data. Good, no? I broke it. It's not coming back, it's tough. So we have I can yell. It's back. Back?
No, red lights.
Yeah, I can yell.
Well, we have another mic. Yeah, do you want to use that?
This?
No, it's not on yet, but do we open
Sure.
it? Absolutely. We'll switch it after this intermission.
Yeah, so you can metabolize everything that I talked about so far. Can you hear me? Okay. So to get at like the information that whatever we're removing from Nordic, after we apply Nordic, we can compute. We can look at the Nordic residual. Here I'm talking about subtraction, but it's not really a subtraction because this is an operation that has to be performed in complex space. As you move from complex space to image space, there's nonlinear operations. So if you just do a simple subtraction in image space, it's not gonna give you, it's not gonna produce the results that you want to, that you're actually looking for, and you need to go back into complex space and do this subtraction in a clever way. Otherwise, you're really distorting the linear nonlinear nature of these relationships. And so here's an example of a single volume of Nordic residual. So what Nordic removes, and the idea is that if we are introducing blurring in our data, then we should see some sharp structure in whatever is being removed by Nordic. This can be like edge of the brain, it can be some sulci or something like that. Doesn't seem to be anything in this. Maybe there's something here in the middle, maybe here, maybe something here on the side. So what we can do is like average all of our volumes together, and the volumes I'm talking about this with Nordic residual, and they look something like this. So there is some structure, but this structure is largely not completely explained by the G factor, which again is to be expected because it's in the process of Nordic. We're normalizing and then by G factor and then putting it back in. So again, really not many causes for concern so far. And it seems that what we're removing is actually just thermal noise. As you can tell, I'm talking a lot about spatial blurring. I feel very strongly about this. I care a lot about this. This again work by Logan Dowdle. So we published this paper in Neuroimage last year, and looks at there's a more in-depth validation of the impact of Nordic on several data sets across different resolution and paradigm and so forth. And so for these specific data sets, for some of these data sets, we didn't have any visual information or not any meaningful visual stimulation to compute our point spread measurement. So we only looked at this spatial autocorrelation, and we looked at them before and after preprocessing. And then we looked at them for standard data, Nordic data, and also DWID noise, which is another algorithm that's out there available for removing thermal noise. It was originally designed for diffusion, but it can also be applied to fMRI. And then we also compared this blurring to smoothing, because as John was mentioning earlier, smoothing is one of the easiest way to get rid of this thermal noise at the cost of obviously diluting the spatial precision of your data. And so here's what we see. We see that there's maybe a tiny little bit increase in in blurring after Nordic relative to standard. Again, nothing too concerning. A little bit more with the WID noise. Again, nothing too bad. And then obviously once you go to smoothing, you see massive increases in smoothing. If you look at the T values for these different data sets and for these different approaches for dealing with thermal noise, we can see that Nordic is more or less equivalent to 1 voxel smoothing for most of these data plots, except here it's actually comparable to 1.5 voxel smoothing. However, it's not plagued by this blurring that smoothing always introduces to the data. So again, all good so far. And then Logan also computed this residual analysis, Nordic residual analysis, for both Nordic and DWID noise. And we can see that while the average residuals of Nordic, so averaged over time, are very much correlated with the G factor, when you look at DWID noise, you can actually see the sharp structure and the sharp edges that I was telling you before. And then these relate into larger, these translate into larger blurring. I should say for disclaimer that obviously Nordic was fully optimized to our end, and we use the WID noise only as it comes out of the package. So I'm sure that if there was some effort made into optimizing WID noise, you can achieve comparable results. Maybe just a side note, that the main difference between Nordic and DWID noise is that DWID noise has a fixed threshold for singular virus thresholding, so removes the same components across the whole brain, while Nordic instead estimates its threshold independently per patch. So that's one of the main differences, I would say. So so far we talked about what I think of like quantitative improvements. So basically we're doing the same thing that we can do without Nordic, but we can achieve better maps with lesser data amount. But can we also achieve some qualitative improvements? What I think of qualitative improvements. So qualitative change in data, do stuff that we could otherwise not do. So allow functional brain mapping, which should otherwise be unachievable due to the high thermal noise regimes. And so to this end, we push the spatial resolution of our data. This is again 7T data, and went to 3D, get an echo still, 0.5 isotropic voxels with a volume acquisition time of about 3.6 seconds. And here's an example of a single image API as they come out of the scanner. So you can see this image are virtually unusable, highly thermal noise dominated. You can barely see any structure here in the middle of the brain. And then this is how this image looks after Nordic. So obviously we've done a very good job of removing this speckly thermal noise here, and we're retrieving most of the structure in the medial portion of the brain. And this is an example of like 10 standard images averaged together. And you can see again close correspondence. Obviously the averages of the images are a little bit blurrier. That can be due to misregistration, motion correction, and so forth. So it's to be expected. But yeah, I think that was again a good science check, but this is only tells us something about the image API quality and nothing about the functional maps. So for to look at the impact on these functional maps, we turn to our favorite paradigm, and we increased our blocks to 24 seconds to account for the longer volume acquisition time. And that's something that Renzo was mentioning the other day as well. So adjust your block length based on your TI. And that's exactly what we did here. And here's an example of our target larger than surround contrast for about 40 minutes of data using standard 0.5 data. And then here on the right, we see Nordic. Obviously, we can barely see any activation, maybe some here, but nothing really meaningful for the standard data. And obviously with Nordic, we retrieve all the spatial features that you would expect to see. I should also mention that Nordic data are not smoothed, nor cluster thresholded, and nor are they confined within cortical ribbon. And yet we see that this improvement is really very much circumscribed to the cortex when we want it to be. So that's really good, and we're really happy with this. And then a little bit more comparison across different existing denoising method. This was actually one of the reviewers' requirement. But we compare Nordic with white noise PCA, the number 2 cursor, yeah. With white noise PCA, image API on the top. We've got DWI noise with complex data, so with image and phase data. Image, yes, and phase data, output and phase data. Then you've got DWI's denoise run only on magnitude data, and then we have Nordic here on the right-hand side. And you can see that really both DWI denoise and Nordic really lead to the best image API. And here we got maps at the bottom. Again, DWI denoise does a relatively good job. Nordic does a relatively good job. That's a different data set, fewer data. And we can see again the distribution within the retinotopic representation of the target here in blue on the T1 on panel C, with Nordic being the dotted purple line showing the largest improvement on T values. The WID noise in this specific case is doing a really good job, but at a cost of massive spatial blurring, relatively speaking. Nordic is down here, and the error bars are actually overlapping with 0. So in this specific case, the increase in blurring wasn't even meaningful. While the other methods seem to increase this blur. All right. Now, next, I'm going to talk a little bit about the Nordic application on VESO. So this was all bold DPI data, but Lasse, Knudsen, and Renzo have been working a lot on very similar analysis, the one that we did in our Nature Communication paper on VESO data, to understand how you can best implement Nordic on VESO. And so before showing you some of the results, I just want to recap, and probably something that I should have said in the initial slide and I didn't. So Nordic works in complex space. So we can work with DICOM data. We can combine phase and magnitude data to reconstruct our complex space data. It also works with magnitude-only data. So obviously, sometimes it's not possible to acquire phase data. Sometimes they're too noisy, and sometimes it's undesirable. So it can also work with the magnitude-only data. And then we can use noise scans, which are nothing else than the same image API, which we can stick at the end of our scan, where we put our power to 0, and so it basically allows us to really estimate our G factor and our empirical level of thermal noise. Or we can use it without noise scans, where then the thermal noise level is just the theoretical noise level of 1 over square root of 2, which is more or less, well, that more or less is equal to 0.707. So this is a 2x2 design, and Renzo and Lasse had to really figure out how to best implement Nordic on VESO data. Each single tweak can cause different modulation on your percentage change responses. So here's some of the results, and I should mention that when you're acquiring VESO data, there's an additional complication. You usually acquire VESO and gradient anecdote data every second TR. So now you have time courses that are twice as long, and they're interspersed between gradient echo and VESO. And so another decision to be made is whether we're applying Nordic on the whole time series or independently per acquisition protocol. In my mind, it's much better to apply, theoretically at least, it should be better to apply, not much, should be better to apply Nordic independently per acquisition protocol. And the reason is the following. If you think that thermal noise should be comparable regardless of whether you're doing gradient echo, spin echo, or VASO or whatever else. That's fine. That's an assumption that I'm happy with. But what we're doing with Nordic here, we're actually working in a discrete space, right? The number of components that we have is equal to the number of time points minus one, right? And we need to ascribe, it becomes kind of like a binary problem. We need to ascribe each of our principal component to either signal or noise. Obviously, because our time series are discrete and we don't have infinite dynamic range, some of the components will be a mixture of signal and noise, first of all. And the other point is that the relative number of components to the relative number of noise will not only depend on the amount of thermal noise, but will also depend on the amount of signal. So you have 10 components, let's say, right? And then now you have same amount of thermal noise, but for the gradient data, you got a lot more signal than you have in the VASO. So your SNR is different. So the number of components that you'll be removing for gradient echo and VASO will be different. If you're combining them together, you're removing the same components. The benefit of combining the two of them together, though, is that you have twice as many time points, and so you have a larger dynamic range. So there may be benefits on combining, on implementing Nordic on both combined VASO and gradient echo, but theoretically, to me, it makes more sense to do it independently. So this is an extract from Renzo's post, and here we can see original data. VASO data is 0.8 isotropic, I think, if I remember correctly, and with the visual gratings, block design, we can see Nordic implemented here on magnitude data, on complex data, flicking between the two. And for this specific case, we see that the improvement in noise, so the t-values are larger when we're using Nordic on complex data relative to when we're using Nordic on magnitude-only data. And also when we're using noise scans, we seem to be removing more noise than when we're not using noise scans. This is by design, because that's how we design Nordic. We design it to be less aggressive when noise scans are not there. So does this mean that we're going to use Nordic on complex data? That's not the conclusion that Renzo and Lasse reached. They look very carefully at all the data. And they observed some percent signal change drop in some of the cases in some of the implementation of Nordic. So this leads to the question, because what I've shown so far is that there doesn't seem to be any meaningful decrease in percent signal change. But can Nordic remove some signal and lead to a drop in percent signal change? The answer is yes, obviously. Like John said, there's no free lunch. Whatever we do is a compromise. And here's an example of layer profile, again, from Renzo's blog. One can see Nordic data in red, and we can see standard data in blue. This is percent signal change for complex and magnitude data. You can see that in the complex data, for example, here, when we're doing combined, when running Nordic on combined VASO and gradient echo, there seems to be a significant drop in percent signal change in the inner layers, which is something that we don't want to, we don't want. It's not desirable. So Renzo and Lasse spent a long time evaluating and trying to understand what was the best trade-off for them, and they concluded that the best trade-off in this specific case to preserve the signal while removing as much noise as possible was to run Nordic on magnitude-only data with noise scans. So before giving you a little bit of intuition of what's happening, why we're removing, what's happening, and why this percent change is being removed, I have to say that this is not my personal recommendation. Every time that I've used Nordic on magnitude-only data, I've seen that the increase in smoothness, in blurring, it's larger than when we're using complex data. And this is going to be related maybe to why we see this percent signal change. I'll talk about that in a minute. And I think that Lasse maybe looked at the spatial precision as well, and he saw a little increase in this blurring, but they decided that there was no cause for concern. It was not large enough to be worried about, and they decided that that was their best approach forward. And that also makes sense, because if your phase data are really noisy and really bad, they're actually gonna harm your or whatever, your data more so than help Nordic. So yeah, that was their conclusion. Ultimately, my advice is whenever you're piloting your data and collecting your data, maybe try to play around a little bit with Nordic and see which one is the best trade-off for you. So what is this percent signal change drop related to? We don't have an answer yet. We're working on it very hard, and we've got a couple of papers in preparation on this. And we've got three somewhat competing hypotheses. Maybe two of them are kind of complementary, and the third one is a little more out there. So as I said before, maybe we don't have enough dynamic range. We have to ascribe components to either signal or noise. Some components are a mixture of both. They may be ascribed to noise and removed. In doing so, you're removing some of the signal, and this can lead to a % signal change drop. Another case, when the signal is below the thermal noise level, so you have very high thermal noise, signal is better in the thermal noise, you have a component that has both, you cannot even see the signal because it's below the thermal noise level, you remove that, you're removing some signal, and it can lead to decrease in % signal change. And then this hypothesis that is based on what thermal noise looks like. Yeah, so thermal noise is Gaussian in complex space. However, there are several papers, older papers, that show that as you move to image space, this distribution changes from Gaussian to Rician. The main point being that while Gaussian noise averages to 0, so that's got a mean of 0, Rician has a mean of x, of larger than 0. And so if you keep averaging and averaging, you're not actually getting rid of this thermal noise, but you're adding something to the data. So one possibility is that the larger % signal change that we see with without Nordic is actually a byproduct of this averaging thermal noise in image space and the Rician property of the thermal noise. So maybe the ground truth is actually the lower PSC observed in Nordic. And there's a paper on bioRxiv that is very interesting by Manzano Patron et al. Is a diffusion paper, but they do lots of simulation to get to the bottom of this decrease in amplitude with Nordic, using both real data and simulated data, and their conclusion is that the ground truth is actually the lower responses estimate that we see with Nordic. But again, very much work in progress. There is some drop. We're not too concerned about this drop as yet. I think that David Norris also observed this drop, and he presented last year at SMRM, and he wasn't concerned either. The reason why I'm not too concerned about this drop is because while we do see some drops in some cases, the specificity, the condition specificity remains unaltered. So if you have like your contrast target larger than surround, or one task over another task, the effect size either remains the same or even increases because of the lower standard deviation. So for me, that doesn't seem to be something concerning, but it's definitely something to keep in mind. All right, a little bit like practical. This is the wrapper. This is how I run Nordic. So it's just like a little MATLAB script with a number of optional parameters that we can input into Nordic that can make our life easier or more difficult, depending on how we're doing it. So the first two refer to filtering our face images. Again, face images can be very noisy, so sometimes it can be desired to spatially filter the data. The face filter width, self-explanatory, is the width of the filter that you're applying. That's a Tukey filter, actually. And then the temporal phase can be 1 or 0. And if it's 1, it means that the filter is calculated and applied independent at each time point. And this can be beneficial in case of like phase drifts or spikes or something like that. This argument here, noise volume last, indicates whether you're having noise scans at the end of your time series or not. The patch overlap indicates obviously the overlap between the independent patches. That's an important parameter. If it's too low, you don't remove enough noise, because obviously the average across patches is also part of like noise removal. If it's too high, your computational time becomes crazy. I mean, it takes days and it doesn't even finish running. So we found that 6 seems to be a good compromise for this for our applications. The kernel size, you can modify the size of the patch. The size of the patch within which you're performing your local low rank approach. The default is 14 by 14 by 1, so it's a 2D patch. You can go 3D as well. We didn't see much of a difference. I like 2D, but it's just like my preference. We also use larger patches, 28 by 28 by 1. I really like this patch as well. Again, advice is always, if you're interested, play with these different parameters and see which one works the best for you. And these last 4 arguments here are just for saving additional information from your Nordic toolbox. So you can save the G-factor map, and then you can save the residual like I showed you before, and then you can compare, like I was showing in the first couple of slides, the average residual, so whatever's been removed to Nordic with the G factor, and in theory they should be highly correlated. If not, there's something wrong. And you can save additional information. This would include, for example, not only the number of components removed, but also the actual components. You can plot them, you can look at them, and you can figure out what's actually happening. And then you can save your complex nifty data. So this is just basically generating two sets of Nordic data, your magnitude data as well as your phase data, both Nordic. And then you just run this little script. You just need 3 inputs. The file name of the magnitude data, the file name of the phase data, and then whatever prefix you want in front of your data. You run your Nordic, and it doesn't take too long. Even on local machine is really quite quick. That was Team being fantastic at optimizing the toolbox. Another factor which I don't play too much with, and I'm a little weary about it, is the scale factor. It's called factor error. What it does is scales the singular variate threshold. So this factor is set to 1, so no scaling. If you go to larger, so in this case 1.5, that means that the value threshold is going to be decreased by 50%, which means that your denoising is going to be a lot more aggressive. So if you remember the first plot where I was showing the dotted line, which is our singular variate threshold, and that would moved up, which implies that you're going to remove more components, keep less components, much more aggressive and much more blurry. And here's an example. For example, when you go to scale factor to 5, the whole brain is active, and also the percent node change drop is really, really meaningful. And that's again work of Renzo. It's really cool. You can play with this if you want. You can go with lower to be less aggressive. You can be with higher for more aggressive. Yeah, that's another option. Just a couple of sanity checks. When you run in Nordic, you see a bunch of like text printed in your command window, and there's 2 very simple parameters that you want to keep an eye on. One is the range of your phase data, which has to be between -pi and pi. So it tells you what the phase data should be and what the actual range is. So we actually implemented, and by we I mean Steen again, implemented in his toolbox scaling so that the phase data actually automatically scale between -pi and pi. There could be some errors. So that's a very simple way to see whether something is going wrong. If your phase data are not between minus and plus pi, there's a problem. And the other thing that you want to look at is the measured noise, this one down here. So in this case, it's 0.7973. As I said, if you run Nordic without noise scans, this is always going to be equal to 0.707, which is 1 over square root of 2. If you use your noise scans, then the noise level is empirically derived from the data. It tends to be larger in highly dominated thermal noise regimes. It can also be lower if you don't have any thermal noise, if you have very, very little thermal noise. Why this parameter is important is because generally, like from experience, should vary between 0.5 and 1. If you see something much larger than 1, you should be worried, because it means you're really removing everything, and then you're left pretty much with very low fluctuation and really compromising the data. So last part of my talk, I'm just going to show a couple of applications of Nordic to sub-millimeter fMRI. So here we looked at, I think Renzo was mentioning yesterday that we never really look at ventral cortex, it's difficult, blah, blah, blah. Here we're looking at the ventral cortex. So this is like a phase study. We went to 0.7 millimeter isotropic voxels. We went to 2D gradient echo here because we cared about the TR. We wanted the shorter TR. Good, no? I lost the microphone as well. So 2D gradient echo, this is the slab, the way it was placed. So we go both V1 as well as FFA, so fusiform phase area, which should be here. We can also get OFA, occipital phase area. And this is an example of a single image GPI after Nordic. You can see that really the image quality is, I love these 2 images. It looks beautiful. All the specular noise is removed, and the gray-white matter boundary is really highly visible, even on a single image GPI. So that's really nice and really helps with segmentation. Here an example of just one run, 3.5 minutes of data. That's a block design with a phase perception task in this case. And you can see how noisy and how much salt and pepper activation there is before Nordic. And then all this goes away while the spatial pattern really remains in the FFA here, anterior FFA, posterior FFA, and then lower level regions. So then we can perform our cortical depth segmentation. We can get 3 depths. In this case, what we're showing the subjects in the scanner were 2 different tasks. There was a face detection task or a fixation task with identical face stimuli. Even the sequence of the presentation was identical across runs. And we would ask subject to do one or the other task every second run. We estimated our percent signal change at the single trial level. So we had 8 blocks per run, 6 runs per task. So that's 48 trials for each of the 2 tasks. And this actually allowed to perform single subject statistics, drawing on our single trials as opposed to number of subjects. And because of the resulting data quality from Nordic was really, really high, then we actually managed to do so with some confidence. So here's an example of one subject where and this is the pattern that we replicate for all our 4 subjects, where we have larger percent signal. Sorry, this is the ratio between the 2 tasks. So face task over fixation task. One, as I said, one was a face detection task, where participants were instructed to respond to their perceived faces in the screens. There are faces, there are no faces. There's no right answer. And the other one's a fixation color task. Performed the ratio between the 2 and plotted this ratio independently per layer or cortical depth, 3 cortical depths here. And we can see that the ratio between tasks was significantly larger in the inner layers of V1 and the outer layers of the FFA. And this was replicated about our subject, 4 subjects at the single subject level. Here's an example of the layers in FFA, in V1, so here, and here is FFA on a single image API. And here are single run time courses. These are just pre-processed, nothing else done to them for the face task in solid lines and for the fixation task with dotted lines. This is V1, this is FFA. Even when you're not doing a face task in the FFA, you can clearly see the activation elicited by the single blocks within a single run. And this is then allowing us to do single trial or single block modeling and do our single subject statistics. And here's an example of the maps. This was again worked by Logan, all the segmentation here. The layer segmentation was done by Logan. And I should mention, actually, maybe that's besides the point, but it picks up on what John was saying earlier, that here, instead of doing distortion correction on the API, we distorted the T1. We did not acquire T1 weighted API. We acquired an MP range, in fact, an MP2 range. And then we use a reverse phase encode to distort the T1 weighted API, so to put it in the same space, or the T1, the MP2 range, the T1 weighted image, put it in the same space, and then co-registration was then really easy. We went right-left in this case, and we placed the field of view in order to try and avoid big distortion to be in region of interest. So it's here, we don't really care about this region. This is the singularity that we're talking about. So our approach in this case was trying to cleverly place our field of view so that this distortion would occur in areas that, in this specific case, we don't care about. We also acquired a reverse phase encode, as I said. So if we wanted to look at these areas with distortion, we can perform our distortion correction in the API, and then layer segmentation, and then go on and perform our whatever analysis we're thinking about. So just, as I said, here is just the same thing that I'm showing here at the bottom. Is the average order of 4 subjects. We got bold evoked responses for both tasks and the ratio. And here are the map for this ratio in V1 and FFA. Blue means low ratio, yellow means large ratio, and you can see here the yellower as you approach the white matter for B1, and instead is yellower as you approach the outer surface in FFA. This is consistent with theory of feedback exchange between higher outer layers and inner layers. Is also consistent with the idea of apical dendritic amplification as a key mechanism for conscious perception. So it's under review. Hopefully we'll get it at some point out. And it's also on my archive. And then 10.5, that's what John wanted to see. There's no layer analysis here yet for reasons that I can disclose in a minute. Mainly it's because we've had issues to get flat enough B1 and also B0 to get reasonable MP range or T1 weighted API images. We're good now, but when I acquired this data, we didn't have functioning T1 and 10.5. So there's no layer segmentation. But we did run Nordic. These are 0.4 by 0.4 by 0.6 voxels, so anisotropic voxel. Voxel volume is more than 1 microliter. And you can see that before Nordic, the highly dominant thermal noise regime does not allow to do any functional mapping at all. There's no single voxel. There's actually a tiny little voxel here that is active that you cannot see, I don't think, but there's one. Otherwise, nothing else. And then we can look at the target larger than surround to identify target voxels or voxels that respond preferentially to the target. And we can look at single voxel, and you can see even at the single voxel level, the quality of the time course looks really, really nice in spite of this super high resolution. Our regular resolution is 0.35 isotropic data. I'm not showing you here because I don't think we're quite ready there, but this is a 0.4 isotropic, 0.064 microliter. That's again green echo 3D with a volume acquisition time of 3.3 seconds. And you can really see, and you can really see that even with only 20 minutes of data at this super high resolution at 10.5, we can get really nice. This is a single image API, really nice single image API after Nordic with activation in all the places that we'd expected. I should explain this. This is actually carried over from a previous slide, so apologies about that. We did the exact same acquisition as 7T, and this is some of the retinotopic representation of the target in V2, and is highly active at 10.5 at S7T because SNR was so much lower, we couldn't see anything. And here is the average time course for 10 voxel, exhibiting all the response properties that we would expect in the specific context. That should not be there, so apologies for that. So that's me done. So just concluding right now. So in removing thermal noise, Nordic increases TSNR. Percent signal change remains largely unaltered. However, as we've seen, it can lead to some drops in percent signal change. It increased the precision of single trial or single block response estimate. It does not blur the functional precision of our data, or at least not meaningfully so. It's beneficial across field strengths, acquisition protocols, experimental design, and different cortical regions. As I said, it leads to quantitative improvements, so doing the same thing that we can do with less data, or what I think is qualitative improvement, so allowing functional mapping and resolution that would be otherwise impossible to achieve due to the thermal noise regime. And before I leave you, just very quickly, future directions. So obviously we're trying to further develop Nordic, and we're working on this T-Nordic, which is a version of Nordic that works in Fourier space, and has the advantage of not requiring the amount of data points that we require when we're running Nordic in complex space, in image complex space. And this is like Farouk's data, the one that he showed in stock and that Renzo showed, and we've seen this beautiful data. I've seen this beautiful data many times, and hope so have you. This 0.35 multi-echo data, 0.35 isotropic data. Here we can see a single run before this T-Nordic, and here again, the same single run after T-Nordic, with this insert showing the zoom in this red box here. You can really see how well you can retrieve these fine structures here, many veins that are not visible in a single run before Nordic, and the correspondence again with 4 concatenated runs of Farouk's data, which is very similar to what we see here with Nordic. So we're very excited about this because this would allow them to denoise very short time series like reverse phase encodes, for example, like T1 weighted DPIs or multi-echo data like the one that Farouk acquired. And then with this, I'd like to thank you for your attention. The collaborators, obviously, Steen was pivotal in developing the Nordic algorithm, and Logan did a lot of the work. Thank you.
Yeah, no, you're doing good. Yeah, we're a bit over time, but it wasn't your fault. I think we started your talk late, and so I want to give you time to